So, welcome back everybody. I hope so far that you're finding these webinar type tutorial sessions quite useful. If not, yeah, I'm always open to recommendations to changing these. This is a very new thing for me, and hopefully I can try and get it right. Now these are an extension to the notes that we did before, which was the first order systems. These notes are up on Blackboard. I would strongly recommend that you get a good grits with them, take a good look through them, and you'll understand exactly where I'm coming from with some of the things that we're going to do today. Now, conventionally, what we'd done before is we'd looked at what happens when you have a spring and damper system, just as a single numerical integration method. This leads to the first order response, and that's what we're looking at. What we're going to do today is perhaps we're just going to go that one extra step. We're going to start looking a little bit more at order systems, but we're going to look at a second order system. It's particular what you can see now, which is a spring damper and a mass or a mass spring damper system. Some interesting elements about this. I'm going to scroll through this quite quickly. I don't want to heighten too much about the deriving these equations. I just want to pick up your interest in specific points. Now, like before, we need a zeta. Now this is the damping coefficient calculation. You'll notice that there's a little bit more of an extension as to our last methodologies of doing it. As with our last one, we simply chose it. This is slightly different. Another important thing, right? If you remember in our last one, it was y is equal to yn is equal to y plus h, all multiplied by the present state of our dy by dt, our rate of change. What you'll notice now is we've got an extra element. We've got mass. But what you can see is that if I chopped off mass completely, you can see that we're back to the initial same state again. We're just using Newton's equation of motion, but what we've got with that mass is we have that second derivative. Now what we're going to do is we're going to play on that. We're going to have a fiddle around with that, and we're going to model this system in Simulink, and we're going to tune it. Boom. Anyway, right. So again, it is worth going through these. It is worth just having a look at how these are particularly derived. This in itself uses Euler's technique. Beauty is with MATLAB, we've got a free, well, in fact, I will show you. So what I'm going to do is, let's get right into it. I'm going to go to MATLAB. So I'll give you a second. Excuse me. God, full of wind as ever. Right, what we're going to do is we're actually not going to do any scripting. We're going to move a little bit more aggressively into Simulink. I think what we can do is we're going to look at two independent systems that are presently stored in Simulink, and we're going to look at two alternate ways of modeling the same goddamn thing. What's important though is that you have a feel as to why we're doing this, rather than just yeah we're doing that because it's good. So let's give ourselves some values first. Now I'm going to use some variables. Makes life a bit easier. Follow me with this. May not make sense at first, but follow me, and we will slowly get a good understanding as to why. So I'm going to say C. C in this case, if you remember, is the damping coefficient. Damping coefficient will tend to be in a ratio of what your spring stiffness is, so they'll be very close to each other in a lack of a better word. So what I'm going to do is I'm going to say 0.5 for my damping coefficient. Again, we can tune this, so if I put this in and it goes crazy, we need to tune it, obviously. Okay, I'm going to set that to 1. So let's give it a mass. Now, given the size of what we're looking at, we're not talking monstrous mass here, so I'm going to say 2 kilos. And we're going to need an initial position. Now, if you think about when we did the first order system, we needed a reason for this thing to be derived, a reason for this thing to be moving. So what we need to do is do the same thing again. So we'll call this y0. just for an initial point in space. Let's set it. Now we're keeping it nice and easy, so let's say 1 meter. Let's face facts. That's a big fucking offset. Right. Anyway, so let's move on to the next bit. So we've now got our variables to control the system. Makes life so much easier in this. But again, I'm just going to call this back up. And I can find it. Where have you got? There we go. Let's just bring that in a little bit. Let's just examine that again. We have Y, the kinetics of Y. We have the damping and the spring stiffness, sorry, of Y. Then we have the damping, and then that damping gives us, we do a rate of change on that damping, and then we have the mass. And we have a second derivative on there. Now, one thing that we know, the S value, again. Now, we did it on the last one, if you remember. It's input over output. It's output over input. I always get that one mixed up. Output over input, and it's always a ratio game. So when we put this in, we need to think about that as well. And also, on our second stage, we're going to need to tell it a present point in space, if you will. On the first derivative, it's obviously going to be set as 0. But let's move on. Let's move on and start building. So back into MATLAB, I'm going to go new. On new, you got Simulink model. Let's go Simulink model. Now this is our first intro. It's kind of like we have templates built all over. Until you feel comfortable, I would ignore them for the minute. Once you feel a bit more comfortable, they are really, this area, I personally found whilst doing PhD, really, really useful. Because if you want to branch out, let's say you're a mechanical engineer and you're thinking, no, I want to get more into aerospace, these block sets, you can't look and go, holy shit, these are really, really helpful. I never realised that the software could be so helpful. But I'd always recommend this after you get a bit more comfortable, because at first you'll just be hitting buttons, hoping that you get the right value. So what we're going to do is, I'm going to go blank model. 1 second. Sorry, it looks like I left my WhatsApp open. So I'm going to go blank model. Let's just make it nice and big. Now let's just remind ourselves about this system. This is our golden area. This is our workspace. This here, you can make anything. If you want real data coming in, you can do it from this point, from this spot. If you want to simulate, I don't know, a car crash, which is weird by the way, but then you can do it from this spot. If you want to simulate any sort of mechanical to electrical to hydraulic system, so you've got a lot of fluids, or you've got a lot of electrical current passing from the actual system through to the mechanical system, you can do that from here. So this is where all the action happens. Now, what we're going to purely center our first model on is Simulink. Let's just open up the Simulink library. Now here, notice on the library browser, I'm going to open that up. Just to make life easier, let's snap it in. So now we've got our blank model, we've got our Simulink library, and we're looking pretty good. So what we need to do is we need to think about what we saw. So we know that there is two integration methods. There's two integrations that occur. So you'll see here I'm on commonly used blocks. I'm going to drag and drop an integrator. That's my first integration. That is my first dy by dt. I'm going to drag and drop a second integrator. So what I'm actually trying to do is I'm trying to model how the equation functions, so I can tune, I can play around, I can even use this in a bigger, grander scale model. What I may do to help those who have never done this before is I may just model a very simple equation, and then you can try and get used to that as well. Because I appreciate at first when you first open this, you think, I have no idea why I'm doing this. But what we'll do is examine these blocks before we start building them. But let's just get everything together first. So we need an S. We need a static sensitivity. So I'm going to drag and drop a gain. Now this gain in essence means that it will function itself, it will change, it will have a gain, it will have elements about it that will be interchangeable. So it allows me to affect certain elements to it. So I'm going to drag and drop another gain and another gain, mainly because we have static sensitivity. Other elements about this system that will change will be the spring stiffness and also the damping. So let's just get you into some sort of organized state, just to put things around. The other thing is as well is we're going to load this system. We're going to put an initial point in space. So like we said that y0 would be set to 1 meter. So this thing is already offset and it's ready to go. And what this will do, what the spring and the damping will do, is they will degradate the system, if you will. They will break down and they will cause it to return to its initial state. So what that means is that when these start to pass through these two here, we're going to need something that will allow it to subtract. So in essence, whilst these two are passing through, always subtract it from the system, allowing us to have the starting to the finishing position. So let's go back. Now, if you look under Simulink, let's scroll down, scroll down, scroll down, scroll down, scroll down, get to math operators. Let's jump into there. Love this spot, by the way. So easy. Now, let's have a look what we got. Sine, sine squared, wave functions, slider gains. Slider gains, I tell you, once you get into this, slider gains are so useful. Like a little slider bar that you can, in essence, kind of like a variable resistor on a pot that you can just change. Oh, it's magic. Right, let's find subtract. I'm looking for subtract. Simple as that. Ah, there. So I'm going to drag and drop a subtract. Now, when you drag it in, what it actually does is says, right, you've brought me in. Would you like to change the signs? And my answer is, hell yeah, I'd like to change the signs. So I want a minus and a minus. Purely because whatever comes in, I want it to just continually degrade the system as it's passing through. So I'll put that there. Right. Now, if I click on the gain, press Control, press R, it allows me to flip these blocks round. This shortcut, by the way, is golden. Really, really useful. Right, now if you remember, I don't know if you've seen the introduction, but let's say I'm all zoomed out here. I'm thinking, I can't do shit with that. I can't see anything. Press spacebar. Boom. Now what I've got is a nice overview. I can see everything. Makes life so much easier. Happy days and all that pizzazz. Okay. Right, so let's think about it. We know that it's going to be degraded. So I'm just going to connect. I'm going to left click, drag and connect. Now we're going to connect the spring and the damper up in a minute. I just want to think about, as it's passing in, what's going to be happening. The static sensitivity is always going to be unchanged. It's going to have changes about it, but it's going to really be unchanged. So what we're going to say is, because it's output over input, it's actually, in this case, it is 1 divided, ready for this, by the mass. Now you see this here? This is brand new. It didn't always used to do this. But anyway, it now just says to you, is this what you meant? And it will always default itself to the desktop. And I put M there because if you remember at the beginning, let me come back to here. At the beginning, I actually put mass in as 2 kilos. So, hell, it's like I planned it. Now, where are we? Where are we? There we are. Oh, I've lost my... oh, there it is. Oh, yeah, I'm going to get there in the end. Took me time. It was worth the effort. So, now we've got 1 over M. So, again, it is the output over the input. So, I'm going to click Apply. So, just for argument's sake, I'm going to call that S. Then, this is where the magic starts to happen. We know that the damping is on the first position for its integration. So we're going to connect these two together because we're looking at the rate of change of the damping after it's been numerically integrated. So if I double click into integrator, what we got here is typical outputs really. We can choose it. See how we have here initial condition source. I can actually change that to an external, and this, if I click apply, this will allow me to manually input an external. But if I go internal, you'll see here it has initial conditions. So there is actually two ways of doing it. In fact, some of the notes that I'll upload about modeling this type of thing on Simulink, you'll notice I actually did it the other way, and I just thought that this would add to further understanding of what was happening. So what we'll do is let's just drag it over a little bit. I'm going to give it some space. Now I'm going to connect these two numerical integrators together, but here is where I need to think about the damping. Don't forget on the equation, the first numerical integration is damping. So let's just bring it in, bring them two together. In a second, I will take you through the different methodologies that MATLAB uses, so you're aware, so you can see the different ODEs that it uses, because it uses about 40 or 50 different tabs, and it will select ideally to what you need it to be. If you're wanting to match exactly against Euler's, I will show you how to actually pull and specifically tell the system, ignore all the better ones, just use Euler's, but I'll show you how to do that. Right, so before I move on, I just want to change that. Let's call that C. You can put damping if you wish, whatever you prefer, so I could put damping. Whatever you prefer, whatever works better for you. So let's bring that together, and I'm going to put that there. Now, if you remember on the desktop, we've actually defined damping already. So I'm going to double click in, and I'm going to say C. 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 We've got C straight on. Now it's reading from the desktop. In essence, this simulation now is being controlled through variable. So it means I can collate all of my variables together. If I have a 100 to 50 to 150 variables that are controlled within a simulation, if I can collate them together, it means it minimizes possibility of errors, possibility of incorrect values added, anything like that. It makes life so much easier. So it's a great way to move forwards with it. You don't have to do it that way. If you prefer to just manually input the numbers, that is perfectly acceptable as well. But I prefer it like this just because it allows me to kind of think, okay, yeah, no, I understand. Right, on my second integrator, don't forget on my second integrator, this now needs to have an initial condition. What was the initial point? So we know here we're setting it to 0. This in essence becomes our range, if you will. And into the second, what we'll say here is y 0. This is new. This is so cool. I like that. It's so cool. So that's 1 meter. Again, bit big. Totally understand. So what we're going to do is bring that round and connect that up. So we know this is spring rate. And we know that it is K. K. Again, let's connect that up. And amazingly, that is solved. Amazing, right? I was amazed too. So that is the full system pretty much solved. The only thing that we cannot do at this point now is we can't get any results yet. We will, but we can't yet. Because, I mean, first thing first, let's save it. Because if we don't save it, this could easily fail. So don't forget, no spaces. What I will do is I will call this spring mass No spaces, spring damper, no spaces. So now we're saved, let's run it. Now it looks like nothing's happened. A lot has happened, but it looks like nothing's happened. Purely because there's no scope attached to it. It actually doesn't know. It's just gone, yeah, I solved it for you. Aren't I smart? So until you say, I want to look at this point, or I want to look at this point, it won't give you anything. So what we need to do is come back into the Simulink library, go to the commonly used blocks, and let's drag and drop a scope. And we're going to actually output of 2 outputs. Let's bring it back up. Let's align it to here. So I'm going to take that, and I'm going to take that. In fact, I'm going to show you in just a second as to what it is that we're actually plotting, why we're plotting it. That, what the hell good is it? So let's bring it back together and let's run it. Okay, so let's open up the scope. Okay, now this is an interesting one. Look at that. Not clear as to what in the hell that is. I mean, it looks very lovely. That in itself, for a start, literally says your data sample's way too small. It's like, okay, data sample's too small. So what we do is we run it for a little bit more. Let's come back onto the model, look up here, our time frame. This time frame will allow, I could set this to infinite if I wanted to, but I know this is going to settle. So what I'll do is I'm just provisionally going to put it to 30 seconds. And if I bring back up my plot again and then hit run. Now, looking a little bit more like I wanted it to, looking a little bit more like it's getting solved. Again, arguably, if you look to the end of where it's oscillating, still not settling. So I'm just gonna add another 10 seconds. I think in this case it really does help. Arguably, you could probably add another 10. But what we got is we've actually got 2 things. So my question is really, what do you think you're looking at? And if we, I mean, the issue is as well, they're over the top of each other. You can clearly see that they're related, obviously from the same system. But when I'm in this type of state, I don't always like things over the top unless there is a direct reason for comparatives. But if I split these 2 up, so if you look here under configuration parameters, I'm going to drop this, and if you notice there, what we've got is layout, and here I can have loads and loads, but all I'm actually interested in is 2. Now what we've got is complete breakdown of the 2. It allows us to do so much more. What we're actually looking at is velocity and position. So there's a few ways of getting a label on there straight away. So let's just stretch that out a little bit. Let's get it labeled. Once we've got it labeled and we've got axes on there, it will help for your learning to remember. Then let's look at actually using our particular solvers and which one we want to use. Hell, we might want to use whichever we want. Runge cutter tends to be the most common one that gets used on these types. But you'll notice here, you see this little symbol? Auto, ODE, is equal to 45. Auto means it will go through every single solving methodology that's on there and choose the most adequate for the actual job. So, first things first, let's get this labelled. The first tab here. This is actually first rate of change, velocity, and this one here is actually position. So you notice what I actually did is I clicked on the tab that connects to the scope and just double clicked it. So I double clicked it and it allowed me to type it in. And if I go back to my scope, then run it again, what you can actually see now is the position and the velocity being labelled, which is very nice, very useful for things like that. Now, we've got as output, we've got a relative area for tuning. I mean, it responds like we want it to. We can change these, but let's just look at the ODE solvers. Let's just be clear about where these sit. So what I'm going to do, and another thing as well, before I move on, another thing is, look at these spikes here. Look at the spikes there. These spikes would imply that there is not enough data being recorded to actually give a true representation of the system moving in space. This can be a huge pain in the ass, and you kind of look and go, that could be better. That could be so much better. So what we'll do is we're going to introduce a little bit more definition. So let's look at how this is actually solved first. Let's go simulation. Now on the toolbar, again, go simulation. And we're going to go model configuration parameters. This is everything. You are now at the helm of what MATLAB Simulink itself is controlled by. Now, variable time step. If you are interested about variable time steps and how these are selected, I recommend K.A. Stroud, Engineering Maths. I know you've all swallowed it a million times, but some of you probably even own it. I think, if I remember rightly, something like 500, page 500, and it denotes about the methodologies for predictor correctors. Variable time steps refer to this. Now, if you remember on our last iteration, what it did is we chose a time step and we looped and looped and looped until it actually hit it. Now, the variable time step is all based on looking at the rate of change between two time steps and seeing if there can be statistically an alteration to make it better. If you're doing verification through equation and you just want to make sure that what you're doing is correct, that there's no real issue there, or if you're doing data acquisition and the data acquisition is set to, I don't know, 1,000th of a second, and you want to be able to map exactly to what you're getting, variable time step will not be for you. This can be a huge problem. So what we'll do is just look at what happened. In fact, first things first, let's just drop the solvers. What you'll see here is all the different solving techniques. Those of you in motorsports, you'll know of Adams. Adams is a solver that is used in in the Adams software itself. This is an MSC thing, and MSC are very much on the ball when it comes to that type of dynamics. So MATLAB has it in there. Interestingly though, it's through variable time step. It is not a fixed time iteration. In fact, let me just close this just for a second. We'll come back to that. So let's just drop it and let's go fixed time step. This now changes. Fixed time step now, we're in a different position of where we're saying we're not using our variable option. We're now going to make it fixed to an iterative process. So if I now drop here, what you'll notice is this now becomes equation methods that use that iterative process. So runge cutter, diamond press, but if you scroll down a bit, you have Euler, Euler, whichever which way you say it, that is in particular to the solver that we can use. Or you can have it to automatically select. But again, if you're doing verification through equation and you've chosen, say, a runge cutter, you've chosen the runge cutter method, this will allow you to map exactly against what you're getting. And if there's changes there, you can actually look to obviously refine and make it slightly better. And then if you wish, you can then shift back to your auto selection. Now the solver details. This is quite interesting, right? So because it's set to auto, it will define itself to a minimal division of the finished time step. So it typically, if I remember rightly, it's I think it's 1,000th of a second. That's normally the auto selection method. You can in particular set that. It depends again exactly what you're solving, but if you're needing to do verification, you will need to set that. You will need to say exactly what it will be. So let's just bring it down. Let's just choose Euler. Again, so in Euler, if you think to our first order system, we would need to move back. We would need to select Euler. We then need to give it a particular time step. This then essentially matches exactly what we were doing in the first order system. So that's just a brief overview as to the solver, the selections, and how to get it working as you need it to be. So what I'm going to do is I'm going to flip back to variable, because I'm not looking to verify in this one. What I'm wanting to do is just look at what it's given. Now, the variable time step. This is where a lot of mistakes I've seen made quite a few times actually. Maximum and minimum step sizes is an auto. Right, now you have a tolerance. Think of it as, I don't know, producing a fitting. You have a plus and minus tolerance. Now we're only looking at 40 seconds. What it's essentially doing is it will allow for this slight offset of this present state tolerance, which in this case is what, 100th of a second. What it then does is it then moves on to the next. If there's any errors in between these, which tend to appear when directional changes in momentum happen, what it will do is it will just try to find the most ideal solution. Now, because this relative tolerance is it's still very low. Let's not beat around the bush. That is very low. Because it's still only set at that, what I'm going to do is I'm going to beef it up just a little bit. I'm going to go well, quite a bit. I'm going to go to the -5, really tighten it up. Be vigilant though. If you did this on something on like a bigger system, so let's say you were going to simulate a quarter car model, things like that, these things really slow down the PC. I mean, when I was doing the piston rings, I needed to go 10 to the -10, and yeah, it was not the most efficient way of doing it, as I learned over time, but it was a real learning curve for me. So this is something to just be vigilant of. If you're seeing some results, you're thinking, that is absolute crap, I've never seen so much poor results delivered ever. This is something to refine, to really look at and then change. So it's just something to keep in mind. So what I've done, as a reminder, is I've gone variable time step, I'm back on variable time step, I've expanded my solver details, and I've gone to the -5. So let's click apply, click OK, and then run. And look at that. So let's just make that bigger. I mean, arguably we've still got these really sharp elements here, but we can refine a little bit more. We can tighten up a little bit more. I mean, you look at these errors here. So let's just, I'm going to zoom in. So let's have a look. I'm going to zoom. I'm probably going to zoom. Let's first do this area, and then let's bring it over a little bit more. And oh, in fact, look at that. You can actually see it where it's not the most happiest. It's still got that there. I mean, arguably, maybe we should drop it just a little bit more to try and refine it. Because I'm very confident that is not a good response. And even using variable time steps, and that's still struggling a little bit. We can change that and refine that a little bit. Now, finally, on this particular model, what I want to do is, let's say that this plot's really nice, but I want to put this into a document. I want to put this into something that looks a bit more sexy than this, because let's face it, it's horrible looking plot. If that goes into an assignment or into a work document, your boss or you're just going to lose respect straight away. Now, I'm not happy with that. So let's just delete that. I mean, not delete, let's just close that for a second. What I'm going to do is go back to go back to Simulink library. Let's just snap you over here. Snap that over there. And what I'd like to do is I want to sim out. Quick way of doing this, let's just go work. It's already there. Workspace. Now I've typed into the search. I always have issues with this every single time. Now I have a lot of friends who said the same, but anyway. So I've typed in workspace, clicked on search, and we have from workspace or to workspace. From workspace is if you have data that you've imported and you want to naturally feed in, or you've got to workspace if you want to take some of this sexy data that you've done and you want to actually plot it. So I'm going to go to workspace, drag and drop. For this, I'll just call this pause. See where I'm going with this. You can do this for the other velocity as well, but for this what I'll do is I'll just take out position. So I'm going to take it, and what I'm going to do is I'm going to tab onto the edge. There's a few things you can do with this. Different types of saving formats. In fact, let's experiment. So I'm just going to come over here, and I'm going to put that there, like that. And let's run it. So we've got a double time series here. Let's double click in. We have two different states. We have time and the initial data set. Nice. Let's go plot, pause. Now this quickest way of doing it, because when I click onto it, the plot system says, I see that. I think I can do that. So you click on plot, and that is what we end up with. And that, I would more than happy to present that. You look at that as an overall, you kind of look and go, yeah, I like that. I can work with that. That is something that is pretty good for me. The only thing I think is really missing is units here on position. But you'll notice it took position off. So what it means is, if I come over here and then go M, then run it again, and then let's replot it. See what I mean? Now we've actually got a nice plot. I can output that into something useful. I can even do post analysis on this. I can change it. I can put scales onto it. I can do so much more. And when these things are exported and put into a Word document, they just look the biz. So for example, if I go File, Save As, and go Desktop, I'm going to save it as an enhanced meta file. Trust me, I've always found these the best. The trouble is they are super big. So click Save. And I'm just going to minimize you. Look at that. That goes into your Word document. That looks the biz. That looks incredible. Exactly. It's a real pride of the work that you've done. So I'd always recommend it. Always recommend it. I'm incredibly nerdy when it comes to stuff like that. I just love that sort of stuff. So that is part A of our first of our second order system using Simulink. Part B, what we're going to do is rebuild the exact same system, but this time what we're going to do is we're going to do it on Simscape. Simscape is just as accessible, but with Simscape it allows you to do so much more. I hope you found this a benefit. Again, as ever, if there is any questions, if there is anything that you're unsure about, if there's any mistakes that you spot, please let me know, because I am only human. I make mistakes just as much as you guys. But if there's any questions at all, anything you're unsure about, please come and see me. I am more than happy to help. and I hope you found it a benefit, and I'll speak to you soon.